we threw away the gravitons. Because they were decoupling on both sides. But now we can work a little bit harder, and on both sides, keep track of the leading coupling for the gravitons. And if you do the deep ray side, you find that the incoming graviton couples to this operator in the deep ray theory. And if you do that on the other side of the graviton, so the graviton couples to them. So in fact, the way that Guster, Klebanov, and Polyakov talked about the dictionary was really in that way, by actually keeping track of the coupling to the outer field in some sense that you take the low energy limit. And so that's another way to think about, pieces, at least pieces of the dictionary.
But for example, the Zohan,
yes.
You can see that from the logic because it's something that's in front of the
Very good, very good. So you're saying what I just told you about Guster and Klebanov and Polyakov was that already we know the deep ray action has, you say, e to the minus phi trace s squared, and then over in the Ramon sector, there's plus c trace f wedge f. Right, so if you keep track of, again, how the original V-rays interact with incoming dilitons and Ramon fields. So at least for these pieces, I'm not sure. Does this work for all of so for these low energy pieces of the dictionary, that's certainly another way to think about it. Yeah.
We could get most like that sort of the high complex system.
Well, the 5-form flux, actually the 5 forms, let me come back to 1 second. The 5-form flux, I'll come back to 1 second. Yeah. So, there's more operators. There's traces of any number of these scalars. There's a natural again. So this is something which and let's make this traceless and symmetric on its SO6 indices. Then it transforms like a zero harmonic, and in fact, when you match these supergravities flows to the operator dimensions, it has the right symmetries and dimensions to correspond to some shape deformation of the 5-sphere. By the way, you just mentioned the 5-form flux, and there's a lot of mixing. Because of the background of the 5-form flux, the 5-form perturbation will mix with the metric perturbation. It's actually, I believe it's correct to say these modes are mixtures of the shape modes of the 5-sphere with modes of the 5 flux. But anyway, you've got all those, and the simplest example of an so these are all protected. They're all things in the operator book whose dimensions don't get renormalized. The simplest thing, the simplest non-traceless thing. This doesn't map to anything in supergravity, and when you calculate one with the nominal dimension, it's not 0. And so it's the simplest non-protected thing you can write down. And indeed, its dimension is supposed to scale as lambda to the 1/4. And the people who work on this integrability, for the longest time, they were really best at talking about traces of operators that were very, very long, so they didn't have to worry about wrapping around the trace in some sense. And they've recently learned how to think about these wrapping interactions, so they can talk about short operators. And again, there's an ansatz at least. I'm not sure if it's more than that. It's a conjecture for how the entire functional dependence of this dimension from weak coupling up to strong. Also, of course, we can shove in a bunch of scalars into any of these other operators, and they become the Kaluza-Klein modes, the S5 harmonics of these corresponding fields. I think there's one more. I'm going to use I'm going to use various pieces of this dictionary later on. I think there's one more I want to mention. So, in some sense, roughly speaking, the only thing you can do is to take, say, I think the following is true, not much has been done. Take, say, a given set of quantum numbers, like the complete SO6 singlets, and list all of the states of weak coupling, list all the states of strong coupling, and, since levels won't cross in general because of state mixing with all you can say is that, each of these will eventually map to each of these. But it's kind of a mix anyway, and so don't mix a lot. Because you're sure what one that's really. Could Konishi and some other operator cross? harmonic of the mix, the Ramon and Nouveau Schwartz 3-chord fluxes, and then of course higher harmonics come when you throw in more scalars. And again, the dimensions match up, dimension 3, I guess here, and so on, and the symmetries. So, I gave you that homework number 1, which was to find a reason why this reality couldn't be true. And anybody who answered there's just not enough states in the gauge theory to match the string theory, you get a point. It's a natural answer. In fact, this argument more or less appears in Roger Penrose's Road to Reality, I think it is, where he answers problem number 1, and his specific answer has to do with the fact that, as we said, the 5 here is large. And so it's not merely that it's a 5-dimensional theory dual to a 4-dimensional theory, it's a 10-dimensional theory dual to a 4-dimensional theory. And then the question is, where do you get all of those, extra states from the 10-dimensional theory? Well, they come from this. And where they really come from is the fact that you have large N matrices. The secret, of course, is that the field theory has a lot of degrees of freedom because N is large. And when it shows up here is that if N were small, well, once we get to N operators in the trace, since I can write the trace in terms of eigenvalues, and there's only N eigenvalues, once I get to more operators, then the trace ceases to be independent. And so it's secretly large N that's allowing me to write down the high harmonics on the sphere. Now, it's another interesting comment on the non-perturbative behavior in N, which is if N is finite, then past a certain point, these traces cease to be independent operators. And so it seems like there's an upper limit to the harmonic, the momentum along the 5 sphere. And this was nicely explained by McGreevy, Susskind, and Tungus, I think, in terms of the supergravity states blowing up into giant gravitons that wouldn't fit in S5 anymore. So it's another nice example of the non-perturbative behavior in N. Now, as Tom was just mentioning, a black hole state, he said it might be a disordered trace of order N squared fields. Is that the sort of thing?
But they said by paper, this is states that have energy of order N squared. The G equals order.
Okay. It might be products of many traces, I don't know. Also, my statement, I'm just something confused. If the trace is not symmetrized, maybe it's more. I'm like, okay, well, we can get more on that story from Tom when he gets here. So I'm just about out of time, and I'll say one more thing very briefly. I think that many later speakers will talk about what happens when you heat things up. So this will be the only commentary I make about temperature. But of course, in addition to trying to count explicit states on a 1-by-1 basis like this, you can count all of the states by forming the partition function, the thermal partition function, and say calculating the entropy as a function of temperature. And there's this famous factor of 3/4 that in the free field theory, if I copy this down correctly, this is 2 pi squared over 3 n squared t cubed, and pi squared over 2 n squared t cubed. This is free CFT, just counting up the thermal entropy of free fields. There's n squared of them, and this is from when you heat up the gravitational system, it's from the black brane horizon area. And the agreement to form is satisfying. It probably couldn't have failed given other things, but it's still satisfying. In particular, this is saying that the gravitational theory really is behaving like a 3 + 1 dimensional thermal field theory. The touch scaling is kind of built in. What's not so obvious, the n squared. What's not so obvious here, what's a surprise, it really is that as you increase the coupling so when we talk about anomalous dimensions, we have these two possible behaviors. I guess I've erased them now. But as you increase G, the anomalous dimension can get bigger and then maybe turn over, or get bigger and then keep getting bigger. And we don't really have a deep understanding from the field theory of why one or the other happens. And in this case too, empirically, what this is saying is that as you turn up the coupling, the interactions tend to reduce the entropy. They tend to reduce the density of states, pushing states to higher energy. But in fact, for most states, this doesn't go very far, and you end up with this kind of behavior. Remember, most states from this point of view is not just these single particle states we've been counting. It's very dense. It's another branch of the spectrum. It's states which are very dense in the CFT, and even the color singlets lose their identity. you're in the deconfined phase in a sense. Anyway, this is the factor of 3/4. The curious fact that when you heat up the system, its entropy is very similar to its free entropy, and this is neither a success nor a failure of the duality. It's just an observation, because I think we don't really have any independent way to think about the fact that this is what happens. But anyway, but in some sense there is this growth counting of the states on both sides, and this is really counting all the states. Black holes have huge entropy, and even when you count all the states, you have just about as many states in the free field theory. Okay, so I think as far as I thought I would today, I guess tomorrow I'm going to start to calculate some correlation functions, just a few to illustrate the operation of the dictionary. If you act with a local operator in conformal field theory, and then watch the system evolve, I think the Coleman, and I forget all the assumptions, but just basically the symmetry plus conservation management method tensor tells you that if you ask where the energy is at time t later, it's in a ring of radius t around where the original operator acted. And so I have to think about the precise statement. What I'm saying is in the CFT, whatever it was you created, well, at least the energy density has moved out. All of the degrees of freedom, at least in terms of their energy density, live on a circle of radius z. And in the book, using the dictionary, at time 0, you created some field. You created some field on the boundary, and it has now moved it has moved a distance z into the interior. So you can actually track, I think, expectation values. So you can actually, you can. I tried to use this. This problem of how you sort. This is the rough argument. After a time t, on one side of duality, there's no question that the size of the state has grown at the speed of light. On the other side, it's propagated into the interior, the matching distance. Well, counting tells you that. I'm trying to think of how to relate it to the diagrammatics, but subscaling tells you that it's n squared t cubed times some function of lambda, and this doesn't always happen in large n theories, by the way. This theory is conformal. In confining large n theories, since at low temperature you don't see all degrees of freedom, you just have the singlets. You get a phase transition to an n to the 0 behavior. So it's not universal to all large n theories. But here, it's really just, I think, the fact that you're in the same phase as the free theory, and so all you can get is functions of lambda. Why? Why couldn't you go with 1 over lambda before? Yeah, 1 over 1. What if the typical state did the same thing as a stringy state and got heavier in this way? Then all of your spectrum is shifting up as you increase the coupling, and the entropy will be falling. That's a logical possibility, and it doesn't happen here, but it happens in other places. There are for the M2 brane theory, there's this end of the 3 halves, which has no obvious interpretation, but in fact you can get that end of the 3 halves. That has to come out, as I'll talk about, sort of a non-subscaling limit of the theory we started with n squared. So there are cases where the entropy really is quantitatively affected by interactions. And again, no clear understanding of what it is, what it isn't, from the field theory point of view. Again, something which the Monte Carlo people might eventually be able to at least confirm, if not explain. S over A to E. Well, sorry, I haven't heard of A yet, but whatever S does, I assume A was some similar lab. I think we're just successful results to get 0 over A. A is the viscosity? Volume. S over V. Well, I mean, when lambda is strictly quick question, we do actually have some information about what happens when lambda is order n squared. Because when lambda is order n squared, when lambda gets very, very strong, the supergravity picture breaks down, and we get into the dual J theory picture. Does that mean the empty goes up again? It must. Yeah, Yeah. So we don't really talk about this much. It doesn't come up much, but you know, the n equals 4 theory has two strong coupling duals. There's the one where you take g squared n to I'm going to get this right. So there's g squared n, but then there's the S dual theory. The S dual of H squared, where the relative thing is n over g squared. So there's a very weakly coupled regime, which is the n equals 4 theory. There's the ADS theory, where this is of order 1. There's then another transition, this is of order 1, and there is the magnetic, call it, n equals 4 theory. So actually, we do have some information about what happens when lambda gets so large. So this is n squared over lambda. So when lambda gets so large as order n squared, then we know actually what this function does again. But if we first take n squared to infinity and then take lambda to infinity, we don't know anything about what that function does if it goes to 0. Yeah.
I think that makes sense. What you just said, being the order n squared. So the lambda is something that's defined whereby we're in an organic expansion, which is divergent expansion.
Sorry, you mean in the field theory?
Yeah.
Well, but g angle squared is fine. I mean,
g angles is defined, but the idea of talking about lambda is something that only makes sense in an organic approximation, and the organic expansion is divergent. So lambda of order n squared is the place where the one organic approximation is broken. Sure. You can't really talk about lambda. You have to talk about, the lambda. Well, I can talk about. I guess I can rule 1 over g squared.
This is obviously a non-Tocquean statement, and yes, we usually talk about lambda in the context where it's what we're holding fixed. I'm a scientific departmentalist, and I will remove the moderator for today. Data integrity is a hot topic in the industry, and should only be discussed as it relates to LLM testing. The number of computerized data acquisition and processing systems in the pharmaceutical industry is growing quickly, and in parallel, the number of record-generated growth that are linked with the regulated products manufactured by the industry. The situation is even further complicated by the integration of systems, interfaces between the systems, and conversions, calculations, and compression of information that may take place during transmission. Data integrity and its practical maintenance are therefore crucial to the safety of patients and the quality of the healthcare product. By using a risk-based approach and the principles presented today, it is possible to generate meaningful reviews and proof of data integrity. Today's presentation will run about approximately 45 minutes, and it will be followed by a Q&A session. Please feel free to submit any questions you have during the presentation using the questions feature. We will address as many questions as possible during the Q&A session. And in addition, we will also make a recording of this presentation, and you will be notified via email once the presentation becomes available for on-demand viewing. Our speaker today is Robert Porzio. He is working as a product manager for endotoxin detection at Lonza, and his primary focus is on instrumentation and software. Robert has 20 years of endotoxin experience in production, marketing, and sales. Prior to joining Lonza, Robert established his own endotoxin testing distribution company. His professional experience in the field of microbiology has been a huge benefit in understanding the criticality of data integrity in the lab and addressing data integrity in endotoxin testing requirements. And with that, I give the floor to you, Robert.
Thank you, Ingo. I appreciate the introduction, and I'm very glad to be here, actually, because data integrity has been quite a hot topic over the past recent months and years, actually, and I'm glad to talk about it, how it relates to endotoxin testing. Through the agenda, we're going to be talking through a few parts. The first part will be about the basics of data integrity, which is a high-level overview, and launches corporate governance over data integrity in our view of it. The second part will be an introduction to kinetic testing, which is merely the look from going from gel pod to kinetic testing and how data integrity is impacted. The third part will be data integrity components through WinSafetyCL and the toxic detection and analysis software. And the fourth part will be a high-level view of data integrity as we look at as a risk-based approach to your review process through audit trails. So it'll be very in-depth, and it'll be the next step that we're coming out with through Lonza for approaching our customers and working with them on site for their data integrity needs. And following the presentation, we'll have questions and answers. So a view of Lonza's overview, basically. We are a trusted supplier to the pharmaceutical, biotech, and specialty ingredient market. We were founded in 1897 with headquarters in Basel, Switzerland. And we have global operations located in more than 40 major sites. We employ over 10,000 people. As a regulated business, Lonza is committed to data integrity. And from a top-down approach, we ensure that all GXP data are created, maintained, and stored in a controlled and